Okay, hi everyone. So we're going to be starting a new branch of an application of differential calculus known as optimization. So let's take a look at this question here. We have 45 meters squared of material to build a box with a square base and no top. Determines the dimensions of the box that will maximize the enclosed volume. So I just want to point out a few things before we start. The question asks us to determine the dimensions of the box that will maximize the enclosed volume. So already we can start to draw parallels between this unit and the other unit that we just covered on stationary points such as maxima and minima. So I think we can actually use that knowledge really wisely to actually help us answer these questions. But the main thing about optimization is that they're actually more practical than maxima and minima questions. So the thing is, we actually have to construct equations of our own and find the maxima and minima of those equations depending on what the question asks us. So what do I mean by that? First thing we have to do is draw a diagram to represent the situation. So we're drawing a square-based box with no top. So it should look something like a cuboid almost. Okay, that's a rough drawing, something like that. Where the square base, so that means that these two lengths are the same, and the height is different, because we don't actually know if it's the same. Then I'm going to color in the side that doesn't require any thought, which is the top of the box. So we first should construct an equation for the surface area, because that's what we actually have information about. So that would be x squared, since we're adding the base in, plus the four sides around the side, because there's nothing on the top. And that's measured by 4xy, because 4 times xy, which is the measurement for each side. And that's equal to 45. Now we have to actually find an equation for what we want to find out, which is the volume. Which in this case is just length times width times height, which is just x squared y. Now we have to find a way to get rid of one of the variables so that we're working with one variable and we can just differentiate with that. In this case, I'm actually going to get rid of the x in this equation because it looks a little bit easier to do so. I'm going to get y isolated. That means that we can rearrange to form 4xy is equal to 45 minus x squared. So y is equal to 45 minus x squared over 4x. And we can just substitute that into the equation so that's just in terms of x, which gives us v is equal to x squared times 45 minus x squared over 4x, which is equal to, let's just simplify it so it's a lot easier for us in the future, x times 45 minus x squared over 4, which is equal to, and then we can just write this as 45 over 4x minus x cubed over 4. It just makes it a little bit easier to look at. Now all we do is differentiate the function. And we set it to 0 so that we can find its minimum or maximum. So dv over dx, that's notation for the differentiation, is 45 over 4 minus, and then x cubed becomes 3x squared. So that's 3x squared over 4. Now we have to set this to 0. So let me just scroll down more. 45 over 4 minus 3x squared over 4 is equal to 0. I'm going to multiply everything by 4 to get 45 minus 3x squared is equal to 0, which means that 3x squared is equal to 45, x squared is equal to 15, and x is the square root of 15. All right, so now we've got our x value. We have to find a y value because we've got the length of the box, length of the base of the box, which is root 15 units. And now we need to get the height of the box represented by y. Well, that's pretty simple actually, because all we need to do is substitute that into this equation over here and find the value of y that suits it. So we've got root 15 squared plus 4 times root 15 times y is equal to 45, which means that 15 plus 4y root 15 is equal to 45. So 4y root 15 is equal to 30. Let me just get rid of most of this here. It's going to make it easier for us. We divide everything by root 15. It gets 4y equals, and then 30 divided by root 15, which is just 30 root 15 over 15, if we rationalize it, which is just 2 root 15. And then y is equal to half root 15, so it's root 15 over 2. That's the dimension of the height, and the x value is just root 15. Alright, so let's just recap what our answers were. So we have this drawing of the square-based box, and we got our value of x, or rather the length of the base of the square root of the square-based box, as root 15, which is also equal to 3.87 meters in this case. And we got y as root 15 over 2, which is equal to 1.937 or 1.94 meters in this case. Now, if we were to calculate the area, we would do the volume of the box. We'd calculate root 15 times root 15 times root 15 over 2, which you would see to be 15 root 15 over 2. Or we can also write this as a decimal, where the value of 15 root 15 over 2 is equal to 29.05 meters cubed approximately. However, it just really wanted us to find the dimensions of this case, so just writing down this is enough. If you approach it this way with optimization, where you get two equations and you link it to the one that you actually need, which in this case was the volume, you'll be fine. And you'll be able to write it in one variable and therefore solve to find the answer or the solution to that equation. After that, though, make sure you address whatever it's asking. So in this case, it was only asking the dimensions, but sometimes you might need to actually give the volume, so you'd have to give it in this case. To check your work, sometimes the solution, there may be two solutions, and it depends on if it's a maximum or a minimum they're asking for. And you should always use the second derivative test or use the sign diagram to determine whether it's a maximum or a minimum, and therefore pick the right answer. But that's it for this video. Thanks so much for watching, and see you in the next one.